Hi everybody, and welcome to example 4 on page 13 of the workbook. And in this video, we're just going to work through one of these three exercises that they give us an example for, just in case you got stuck and want an idea of how might I do the other two parts. Hopefully this will help you. All right, so let's look at part A of this together. And the question they're asking us is whether or not this contour plot could represent a linear function or not. Okay, so how do we know again that a function is linear? Well, the property that we're looking for is if we choose a constant straight line path, does the slope stay the same? Let's do a little experiment. Okay, so if you move in the x direction from left to right, what do you think? Does it look like your z values are going to increase at a constant, or are going to change at a constant rate? Okay, looks to me like that's plausible because we're getting equal spacing between those contours. Okay, so to go from 6 down to 4, that takes the same distance as from going from 4 down to 2. So we're getting equal spacing, which tells us that we should be getting a constant slope. And what about in the y direction? Okay, well there again, we've got equal spacing between these contours, one by one. So that's an indication that our slope is staying constant. Okay, so based on those two preliminary observations, yeah, this looks to be a linear function. All right. Well, if it's a linear function, can we find a formula for it? That's the other part of the question here that they're asking us. All right, and again, the only formula that we have up to this point is the one that looks like this. I'm just going to write it at the top of the page so that we don't have to keep flipping back and forth. Okay, that's our formula for a linear function in 3 dimensions. So we basically need to find two slopes and a point. If we can do those three things, we can come up with a formula for this. All right, so let's start with the slope in the x direction. Okay, and to do that, one way to do it is to just pick a couple of points. And it doesn't really matter where you do it, but it's convenient to choose points that are right on contour so that we can see what the z values are. So I'm going to call those P and Q. And we're moving in the x direction, so we should be able to measure the slope in the x direction going from P to Q. All right, so the slope in the x direction is going to be the change in z over the change in x. All right, so between P and Q, those 2 points that we chose, how much does z change? How do we know what the z values are? Well, the z values are just the values on the contour. So we started at 4. We were on the contour for 4. We ended up here, and the z value there is 2. So the change in z should be 2 minus 4 along that path. Okay, how much did x change along that same path? Well, that's a little easier to see from the picture. So P, that's sitting here at about x equals -1, and then Q is at x equals 2. So that's going to give us 2 minus -1, 3 units. All right, do the arithmetic, and we're going to get -2 over +3. There's our slope in the x direction. Okay, and for the slope in the y direction, we just want to pick a couple of points, okay, where x stays constant. And again, there are a lot of choices that you have, but it's convenient to choose points that are right on contours. Okay, so I'm going to pick those 2 points and call them R and S. Okay, notice that we're moving just in the y direction and going from R to S, so that should measure the slope that we want. We'd like to measure the change in z over the change in y. Okay, so in going from R to S, what's the change in z? Well, we start at 8 and we end up at 10. Those are the contours that we move between. So we're going to get 10 minus 8 is our change in z. And how much does y change? Okay, well, we go from 2 to 4. So that's a distance of 4 minus 2 over 2. And so calculating that slope, we're going to get 2 over 2, which is just 1. There's our n. Okay, so far what we've got is a value for m and a value for n. The missing piece here is a point on this linear function. Okay, so all we need is one point. we've written down 4, P, Q, R, and S, so let's just pick one. How about if we stick with P here? What would the coordinates of P be? Okay, well, from the picture, we can see that the x-coordinate is -1. What's the y-coordinate? That's -2. And the z-coordinate is just the contour that we're on. That's going to be this 4 that we're sitting here. Okay, so -1, -2, 4 is one point that's on our plane. And we're ready now to write our equation. Okay, those three numbers are just the x0, y0, and the z0. So, going back to this formula at the top and filling in the pieces, we're going to get z equals z0, that's 4, plus our m, which is -2/3, x minus x0, that's going to be x minus -1, okay, plus n, which is 1, times y minus y0. Okay, and if we just maybe simplify that, we can rewrite that as 4 minus 2/3 times x plus 1 times y plus 2. Okay, and there's our answer. So putting it all together, we discovered that the answer was yes, this is linear. And we just found a formula for it right down here. Okay, so see what you can do with the other two problems in this example.